the objective could be stated simply. Build here, on the banks of the Mississippi, a monument to symbolize the westward movement of the United States. But remember the requirements. The monument must reflect the courage of the explorers. It must pay tribute to the sacrifices made by the soldiers. It must express the excitement of those early days during the rush for gold. The monument must contain the spirit of all the men and women who ventured into the wild unknown, thus making the Western pioneers a permanent part of our American heritage. And what of the land? Well, of course, it must be included. The monument must reflect the fascinating beauty of the Great Plains, the shifting sands of our vast deserts, and the majesty of our snow-capped mountain barriers. It must rank in dignity with the Golden Gate and command the respect of our coastal cities. Capturing all of this, the monument is to be erected here, where the West began, on the banks of the Mississippi, in the city of St. Louis. The land, its people, its spirit, are here symbolized by two graceful columns of stainless steel reaching skyward, joining to form an arch of soaring grandeur. Truly, a gateway to the West. This is Brace Gilson, reporting a significant event of our time. The story of the building of the Jefferson National Expansion Memorial at St. Louis, Missouri. On December 16, 1933, the St. Louis Post-Dispatch reported the formation of a civic group to work for the establishment of a memorial to the pioneers of the Mississippi Valley. 2 years later, on September 10, 1935, the same newspaper reported that a bond issue of $7.5 million to finance the city's part of the memorial had been approved at a special election. Since that time, Congress has been working on behalf of the project, the various acts having been signed by 4 presidents of the United States. Franklin Roosevelt in 1934, and later by Harry Truman in 1950. Dwight Eisenhower in 1954 and 1960, and John F. Kennedy in 1961 and 1962. In 1947, public-spirited citizens of St. Louis contributed $225,000 to the Memorial Association to conduct an international competition for a suitable architectural design for the memorial. Among the world-famous architects who submitted ideas was the late Errol Saarinen. He, together with his wife, developed the Saarinen catenary arch. What is it? Watch. This chain is 3 feet long. If I were to move the ends toward each other, spacing them equal to the depth, I have produced the arch design. Turn it upside down. There you have seen the famous catenary arch design, recognized as a triumph of architectural genius. Creating such a masterpiece on paper was one thing, but converting it to reality in the form of steel was quite another. Construction of the arch presented challenges that would tax the ingenuity of the world's most capable and experienced fabrication and construction engineers. Selection of the organization to undertake the unprecedented project was quickly made on the basis of past performance and proven capability. The Pittsburgh-Des Steel Company, better known as PDM, had a reputation for tackling the tough ones. A record that dates back to the company's founding in 1893. Today, PDM has 14 steel fabricating plants strategically located throughout the United States, with sales offices near all major industrial markets. Examples of PDM engineering and construction capability can be found throughout the United States and abroad. Because of its record for reliability and integrity, PDM has been entrusted with many of the nation's most critical construction projects. For example, the building of the bomb-proof shelter at the White House, which will protect the President and the Cabinet. At Cape Kennedy, the extremely critical fuel storage tanks for handling fuel at minus 320 degrees Fahrenheit were designed and built by PDM. The Mariner spacecraft, which electrified the world with its journey to Venus, was tested and proven in this vessel. Outside, the conditions of Earth. Inside, the cold, black vacuum of space. The transonic and supersonic tunnels at Tullahoma, Tennessee, create and contain man-made hurricanes where winds reach velocities of 4 times the speed of sound. PDM also builds stadiums, grandstands, reservoirs, elevated tanks, schools, bridges, process plants, and atomic vessels. In Pittsburgh on Neville Island, headquarters for PDM, they knew that it was this kind of capability that had won for them the contract for fabricating and erecting the memorial arch. It all started with engineers tackling problems no one had ever faced before. The arch, rising 630 feet, is made of triangular sections, diminishing in size as the arch rises. If conventional vertical construction towers were used, workmen on the tower would be up to 200 feet away from the arch, since the arch curves and the tower doesn't. PDM engineers came up with an ingenious answer to that problem. As the legs of the arch progressed, special tracks would be attached to the outside surface of the arch, upon which a huge creeper derrick would climb. Since the tracks curve with the arch, it is necessary to re-level the derrick platform at each new location. The derrick pulls itself up by its own bootstraps, so to speak, through cables attached to the hoisting engines. The individual sections are 54-foot equilateral triangles 12 feet high. The sections will have an outer surface of polished stainless steel, 1/4 of an inch thick. The inner wall of the arch is made of carbon steel plate, 3/8 of an inch thick, except at the 3 corners, where 1 3/4 inch plates are used. These reinforced corners constitute the main support of the arch. The space between these walls measures 3 feet. They are held together by bolts and braces, which are attached to the outer stainless steel wall and bolted to the inner carbon steel wall. Vertical steel rods, called post-tensioning rods, are set in place. These will be joined together as each section is added. Then concrete is poured to fill the space between the 2 walls. This leaves a triangular hollow core inside for elevators, stairways, and passenger trains, which will carry visitors to the top, where the arch finally tapers down to 17 feet at the crown. The concrete between the inner and outer walls will extend up to the 300-foot level. Beyond that, steel stiffeners will tie the inner and outer sections together. Both legs will rise simultaneously, but since the arch is not absolutely rigid, for it is designed to sway about 18 inches, A method had to be devised for stabilizing and positioning the two halves so that the final section could be positioned accurately and welded into place. This will be accomplished by a stabilizing truss, which will be assembled on the ground and raised to position between the two legs. The engineering team now turned its attention to designing the special jigs, fixtures, and welders needed for the fabrication and assembly of the arch. Here's where past experience and know-how really pays off. The dreamers have all had their say. Now the dreams must be translated to reality based on fact and figures. Under the same roof where the arch was planned, it is also fabricated. This requires the last word in production facilities for forming, shaping, bending, and cutting. As an example, here a modern plate shear is cutting the stainless steel preparatory to welding. This welder was specially built for the purpose of joining the stainless steel plates of the outer shell together. The plates, which are received from the mill as 6 by 18-foot panels, are placed on the bed of the welding table by specially developed vacuum-type lifting devices. As you will notice, this bright surface must be protected constantly throughout all of the fabricating operations. When the plates are aligned, the arc of the welder can be struck with confidence. Using stainless steel wire, the welder joins the sections at the rate of 42 inches per minute, increasing the size of the section now to 12 by 54 feet. This constitutes one side of the first section and weighs 3 3/4 tons. The huge plate will be placed, finished side down, on the cutting table, which contains protective padding. It is here where the back of the plate is scribed to exact size. Since the arch diminishes in size as it rises, each succeeding section is a little smaller than the one that preceded it. Stainless steel is tough and hard to handle, so the cutting of the plate is a difficult and demanding operation. This abrasive wheel rotary saw was developed specifically for the purpose. It cuts a square edge at the speed of 3 feet per minute. Edges must be straight and true. Therefore, some operations require that a planer be used. These threaded stainless steel studs are inserted into a welding gun. By employing a template, they are spot welded evenly onto the back of the faceplate. In another part of the fabricating shop, this 18-foot press brake is fashioning carbon steel plates into what we call Z-bars. The Z-bars are now bolted to the studs. Here, torque wrenches must be used, since tension must be uniform throughout the length of the bar. These long bolts brace and space the inner and outer skins and are attached on one side to the Z-bar. After being moved from the table, the section is placed on edge to receive the carbon steel inner plate. This inner plate has been separately assembled and comes to the erection floor with all the bolt holes already drilled. These holes, of course, coincide with bolts attached to the stainless steel plate. In order to slide the carbon steel plate onto the bolts, sleeves, which resemble short pieces of pipe, are inserted through the holes and onto the bolt threads. The The carbon steel section is then inched into position. Spacers are used. The bolts and braces tightened accordingly. After this is completed, the entire assembly is ready to be moved to the assembly area. Since the arch curves as it rises, the sections will not be vertically true. Each one has a specified cant, which is measured in this operation. This is the moment of truth as far as the fabricator is concerned. If the plumb is off more than a few thousandths, someone has made a grave and costly error. Before shipment, all three sides of each section are assembled as they will be at the arch. Dimensions are checked. Bolts are adjusted to bring the corners to their exact specified fit. Nothing, absolutely nothing is left to chance. Remember, you don't make corrections hanging 600 feet up in the sky. When everything has been given the green light, the three sides of the triangle are moved to the shipping area. These first sections are truly gigantic. As you can see, they dwarf the men and the shop as well. Shipment of the sections to the erection site is accomplished by using railroad transportation. Two sides of the triangle are secured and shipped in one car. Again, this securing required special jigs, which were designed and built to assure safe delivery. The journey by rail will take approximately 10 days. The first shipment of sections arrived on time and in good condition. They must now be assembled and welded into a single triangular section, ready for placement on the concrete foundation. A large crawler crane at the assembling area gently moves the huge section to a specially designed flatbed railroad car, which will be used to transport all of the sections to either the north or south erection areas. It takes all the power this large bulldozer can muster to gently nudge this 55-ton section over to its foundation. Here, another crawler crane takes over. Incidentally, before we arrived, much work had gone into this reinforced concrete foundation. Even though you can't see it, it's gigantic, clear down to bedrock. These two crawler cranes are working smoothly together, placing the fourth section gently into place. When we build to a height of 72 feet, or total of 6 sections, we have reached the lifting limit of the ground cranes. So now, we must start on the assembly of the creeper tracks and derricks. This is one of the unique construction features of this job. It looked good on the model and just great on the drawing boards. Now, how will it do in reality? The tracks are mounted on a special foundation, then secured to the leg with high tensile bolts. Next, they assemble and rig the 80-ton derrick with its 100-foot boom and 30-foot jib. By now, we are into the summer of 1963 and are adding the 9th section. You might be interested in the fact that a total of 71 sections must be added to each leg until they meet together at the crown of the arch. Remember, each section must be placed, tack welded, ground, finally welded, and concrete added before you can place the next section. These operations, of course, are being performed on both the north and south legs simultaneously. Although we've just begun, The curvature in the arch is obvious. Looking from the city, this is the north leg, with the Mississippi River just beyond. On the far bank, the state of Illinois, and this is the south leg of the arch. At this point in the erection, we have progressed as far as the creeper cranes will permit. So they must be moved. With each creeper weighing a little over 80 tons, it is only natural that the raising must be performed in a very exacting manner. First, the large pins which hold the creeper to the tracks must be withdrawn. Heavy rigging attached to 5 drum hoisting engines on the ground raise the creeper 48 feet with each move, after which the pins must be reinserted in the tracks. When this move is completed, the creeper will be ready to go to work again, raising still more sections of the arch. We are now at approximately the 200-foot level. The sections are a little smaller in size, and they're also a little lighter in weight. The operator raises them in much the same manner as he did the larger sections, only now it takes about 12 minutes to raise them to the top. As the section nears the top, the workman makes sure it clears all objects, or a touch or bump could cause serious damage. That's the safety net you're looking through. It's positioned a few feet below where the men are working. It's a safeguard in the event a man should fall, as well as to protect the men who are working below. As the triangle is swung into position, you can see the reinforcing bars and post-tensioning rods of the previous section. The back of the section will touch down first. Then, the forward corner will be lowered until the section is within a few inches of being landed. Now we're ready for the scaffolds to be installed around the arch, so the men can go to work. How do you suppose the men get up there? On an elevator, of course. And if you want a thrill, take that ride. Talk about sky hooks. Here they are. As you look around, it all looks the same as it did on the ground. That is, until you move out on the scaffolds and look over. Wow! Inside the arch, work is progressing on the welding of the carbon steel plates, fusing the whole arch into a one-piece construction. Then, these welds are ground down to even the surface and improve the appearance. All welds, regardless of whether they are made on the stainless exterior or inside on the carbon steel plates, must be radiographic inspected. Here, a workman uses a straight edge to be absolutely sure of the alignment before tack welding. Not only must the sections be truly flush, the gaps must be evenly spaced. To assure this, following the tacking, a grinding wheel mounted on the track travels automatically along the seam. The tack welds are also ground down before the final welding is started. Now, additional sections of track are mounted on the stainless surface. These tracks are held in place by vacuum cups, permitting the welding head to travel along the track the full length of one side of a section. Bear in mind that these workmen are doing this two-pass welding operation 300 feet up in the air. Back at ground level, the waiting concrete bucket is being filled for the last time. We have reached our 300-foot mark, about halfway up the leg. So this is where the concreting between the walls ends. When the bucket reaches the top, it is guided into position by the workmen who deposit and vibrate the concrete into place. Today, excitement is running high, for the men have now reached the 530-foot level, which means the stabilizing truss is about to be hoisted into place. There have been changes in its design, but its function is still the same. This will serve as the strut between the two legs of the arch until the final closure at the top. Today, an early morning in June 1965, through the combined use of the two creeper derricks, the strut has been successfully hoisted into position. Immediately, the workmen set about tightening the high-strength bolts, adjusting them to position the strut, which, of course, positions the two legs of the arch itself. It's a beautiful sight, isn't it? Even though it's not finished, I think our forefathers would more than approve. As the summer of 1965 rolls around, it is obvious that the arch is now nearing completion. There are only 20 more sections left to be placed, and the creeper derricks need to be raised just one more time. By October, all the sections but one are erected. That opening you see is only 2 1/2 feet. We need 8 1/2 feet to install the crown. So, special hydraulic jacks are employed, which develop over 1 million pounds of thrust. This force is applied between the north and south legs, causing the 2 1/2 foot opening to spread to a total of 8 1/2 feet. Today, there is excitement in the air, a tension so strong that it's not describable unless you were there. Historians, please note, the year is 1965. The day is Thursday, October 28th. The time is 9:35 a.m. The occasion, the placing of the keystone in the Jefferson Memorial Arch. Because the day is so beautiful, the hot rays of the sun beat down upon the wide back surface of the south leg, causing it to expand. This expansion made the south leg drop 1 foot lower than the north leg at the crown opening. The engineers knew this could happen, and they were prepared. By using fire hoses and water played directly on the south leg, the temperature and alignment was corrected, and the closure continued. This crowning section must be maneuvered laterally as well as around the jacking equipment. These were tense moments because there were times when the clearance narrowed down to less than an inch. Here's how the closing section is finally moved into position. Then the jacks are released very gradually, allowing the legs to come to bear against the closing piece. As the men inside work to secure the keystone, we can sneak a first peek out the window. Great, isn't it? With the arch in its proper geometric form, the engineers breathe easy, knowing that the pressure is now equalized throughout the whole structure. The Jefferson Memorial Arch is truly an architectural triumph, a suitable memorial to interpret for generations unborn, the indomitable spirit of man to probe the unknown and build new empires beyond existing horizons.